Welcome to section 3.2 of Essential Statistics. In 3.1, we looked at measures of center, and now we're going to look at measures of spread. Here are the objectives. Again, this is a good thing for you to hold on to make sure you understand all of these points before the next test. I'm not going to read through this. So, suppose you were deciding between living in San Francisco and St. Louis. One of those considerations you might have is what is the weather in those when making your decision. The table represents the average monthly temperatures in degrees Fahrenheit for both cities. If we looked at the mean temperatures of both cities, we'd find that they're quite similar. There's only approximately 1 degree difference between San Francisco and St. Louis. So this data point doesn't give us a lot of information about the differences between these two cities in order to make a decision or to make some stronger comparisons. However, the temperatures in St. Louis are more spread out than those in San Francisco. So that means there's a greater variance in the temperatures in St. Louis than there are in San Francisco. So there's higher highs and lower lows kind of idea here. And so that may be more of what you're worried about. Is it too hot in this area or too cold in this area? And so again, while the average temperatures are the same, the highs and lows are going to be different between these. And this is the idea we have in this idea of spread and why this is such a powerful idea in statistics. When we plot these average temperatures by month, you can see that, excuse me, San Francisco only goes between 50 and 64 degrees temperatures, average temperatures per month. But when you look at St. Louis, you can see the lowest degree is in the 30s and the highest is in the 80s or close to 80. So this gives us a little more information beyond the idea that the centers of data are relatively the same. The range of a data set, these are the high and low values, specifically the difference between the largest value and the smallest value. And here we can see that the range of the San Francisco temperatures, we take the largest value, 63, minus the smallest one, 51, and we get 12, versus 49 when we take 79 minus 30 for St. Louis. And so this is a whole different concept and a whole different way of describing data and in terms of statistics in describing data related to an experiment or a hypothesis. While the range is often easy to compute, we don't actually use range in practice because it's only picking out two of the data values, the highest and the lowest. And so while this may be valuable in some instances, like we just saw with this idea about moving to a different city and comparing them, it's not always the best piece of information for us to make judgments or inferences or conclusions about our hypothesis based upon the data we collect. When a data set has a small amount of spread, like the San Francisco temperatures, most of the values will be close to the mean or the average value. When a data set has a larger amount of spread, a larger range, more of the data values will be far from the mean. The variance is a measure of how far the values in a data set are from that mean on the average. So it's kind of like an average range, if that makes any sense. So it's like a mean difference or a mean variance, an average variance, etc. And this is getting closer to the concept that we use in statistics known as a standard deviation. Okay? We do calculate the variance differently if we're dealing with a population versus a sample. Okay? So we're going to look at those. And again, this is based upon a sample being a much smaller subset of the entire population. So we have to make some mathematical adjustment for that. So when you're looking at these values, this gets a little confusing. This is math notation, x1, x2, x3. These represent the data you collect from your experiment. So, and this is a population. So let's say you were calculating people's blood pressure. These would be all the blood pressures you take. Maybe you're taking a survey. X1 would be the number of people that responded X1, number of people that responded with an X2 solution, etc. And then, of course, the size of the population is uppercase N. And remember that mu, this Greek letter mu, denotes the population mean or average. Okay, so in order to find our population variance, that's represented here by the lowercase Greek sigma letter, and it's sigma squared, not sigma 2. What you do, interestingly, this is a math sigma sign. You take each of the data points, subtract the average value, the mean, you square that value, then for every data point, you add them up together. That's what this mathematical sigma means. So we take x1 minus the average, square it, plus x2 minus the average squared, plus x3 minus the average squared, plus x to the n minus the mean squared. All those differences squared, and then we divide them by the population size. Okay, and this gives us the population variance. Again, simply subtract the mean from each data point, square that value, add all of those squares, and divide by the population. This is just notation saying take the mean, take the difference, square each of those, and then add them all together, and then divide by the population size. If we actually take the square root of this, we just get this symbol sigma, which is the standard deviation, which is what we're typically using in when we're doing statistics. So let's look at an example here. We want to calculate the population variance for San Francisco. I'm sorry. We want to calculate the population variance for the San Francisco temperatures with the population average being 57.5. So if we added these all up and divided by 12, we'd get 57.5. Now remember, for the population variance, we take each of these values, subtract the mean, and square it, and add them all together. Okay. Here the mean was already calculated for us. Again, we take each data point, 51 minus 57.5 squared, 54 minus 57.5 squared, 55 minus 57.5, then squared, 56, etc., all the way down to 52 minus 57.5. Again, that difference squared. Once we do that, we're going to add them all together. Here you can see it. So we have 51 minus 57.5 gives us negative 6.5. When we square that, we get 42.5. We go through and do that for each of these values, take the difference between the data point and the mean, then square that difference, and then we're going to add all of those up, basically adding up the bottom row here, and we get 169. We divide that sum by the population, In this case, we were doing all the months, so the population is 12, and so we get the variance equals 14.083. Now let's look at sample variance. When the data values come from a sample rather than the population, this is called a sample variance. The procedure for computing the sample variance is only a little bit different. When you look at the formula, you'll see that the difference is really in the denominator. So here, remember that the average for a sample is x bar, it's not mu, which is the population one. And again, we have the same notation for each of the data points, x sub I, which would be x sub 1, x sub 2. We have a lowercase s talking about the sample variation. And then in the denominator, we have the lowercase n, which is the sample, the size of the sample. But notice we use n minus 1. Okay, and again, the lowercase s squared is the sample variance, and just the lowercase s would be the standard deviation. In population variation and population standard deviation, remember we use the Greek symbol sigma. And that's a pretty much standard notation thing across the board, that population uses the Greek letters. And then for samples, in most cases, we use alphabet characters. So the big difference here is that we're dividing by n minus 1. So remember that when we take a sample, we're taking a small subset. And so we have no guarantee that the results from the sample are going to be comparative to the results if it were possible and if we did do a data study on the entire population. And so it turns out that the deviations using the sample mean tend to be a bit smaller than deviations using the population mean. That is to say, if we were to divide by n, lowercase n, when computing a sample variance, the value would tend to be a bit smaller than the population variance. And it can be shown mathematically that the appropriate correction is to divide the sum of the squared deviations by n minus 1 rather than n. You don't really need to know that. It's very common sense, right? We're taking a smaller subset of data. It's likely or it's possible that data is further spread, etc. So we want to correct for that smaller sample, smaller data points, and this is the way we do the correction. Again, is by dividing the standard deviation and ultimately the standard, the sample variance and ultimately the standard deviation by n minus 1. So let's look at an example here. A new type of battery is tested for laptop computers. The lifetimes in hours of 6 batteries are 3, 4, 6, 5, 4, 2. Find the sample variance of the lifetimes. You've got the formula here. Again, this is telling you to pause. So calculate your x mean, your x bar, which is the sample average, very simple. And then, walk through each of these values. Each data point, there's one here too, don't miss this one. So 3 minus the average, 4 minus the average, 6 minus the average, each of those squared, and then add them all up. Making a little table is usually best. Finding each of the values, then finding the average, and then doing the difference, then squaring that, and then adding them up, and then n minus 1. Since we're looking at 6 batteries, n minus 1 is going to be 5. All right, so hit pause, try this problem, and see if you can find it. So I'm continuing on. If you hit pause again if you want to try this on your own. It's a good idea to practice these problems while you're watching the video. Every little bit of action you take makes your recall better. So again, we add all the battery values divided by the number of batteries, and we get a mean, an x bar of 4. So again, what we're doing is we're taking each of those value points. The first one is 3 minus the average squared. 4 minus the average squared. 6 minus 4. That squared, each of those value points minus the mean squared. And then of course it's all over n minus 1. This is pretty easy to do because we have -1, 0, 2, 1, 0, and -2 squared. So each of those squares is pretty small. And then of course it's all divided by 5. When we add all those values together, we get 10 over 5, or 2. This is the sample variance. If we wanted the standard deviation, we would just take the square root of 2. Because the variance is computed using squares, specifically squared deviations, the units of variance are also squared units of the data. This is just like when you measure, like let's say a room to put it on carpeting, you have square feet instead of just feet. The measure of the walls or the length and the width are feet, but when you measure the area, you have square feet. It's the same with the variance, so it creates a different kind of idea. In most situations, it's better to use a measure of the spread that has the same units as the data, because it can also be confusing, especially when we're doing data collection, what a squared unit might represent. In the example of a room, we kind of have an understanding of what area is and generally contextual, but it could be quite confusing if we're trying to figure out the area of a virus versus what's the performance of that virus or whatever experiment data unit we're using. So it's generally a good idea to have the measure of spread the same unit as the data, and we do this simply by taking the square root of that variance, and that this quantity in either case is called the standard deviation. So again, we have the same units. The standard deviation of a sample is denoted by lowercase s, and the standard deviation of a population is denoted by lowercase Greek letter sigma. Okay. The population variance of temperatures in San Francisco was calculated to be 14.083. So the population standard deviation would be the square root of this, or 3.753. Again, when you look in your textbook has instructions on how to find these measures, statistical measures, using technology, whether you're using Minitab, Excel, which you do have Excel homework now, so you can also check your the back of each section in your textbook for how to do that with Excel when you're doing that homework. And of course, you're allowed a TI-84 calculator on all tests and homework. Okay, so go to your textbook or just go online. You guys are really good at Googling stuff or doing AI, and you can find out that specifically for Excel, the reason there's Excel homework in this course is that Excel is probably one of the most widely used statistical tools, and then just kind of data analytic tools used across all different disciplines of work. So it's a good idea for you to know and to have some exposure to Excel, which is why I created those specific assignments. Again, I highly recommend you spend some time looking at these again in your textbook. I'm not going to be teaching that specifically, but you have your textbook, you have online, and then you have the homework. Remember that a statistic is resistant if its value is not affected by extreme values, really large values or really small values in the data set. Standard deviation is not resistant. That is, standard deviation is affected by large values, extremely high values or extremely low values. Well, that kind of makes a lot of sense, right? Because standard deviation is this idea of variance. And so if you have really large or really small values, you have a greater variance because your data is more spread out. So standard deviation, even by the definition of it being a measure of spread, it just doesn't make sense that it would be resistant, because the idea of resistance is that when you have spread, a larger spread, um, that data point doesn't really get affected much. That's if it's resistant. But of course, if you're measuring spread, if the spread is larger, your measure is going to be larger. So the idea of resistancy for standard deviation doesn't make any sense. It's kind of counterintuitive. Here's just a sample problem. See if you can calculate the sample variance and the sample standard deviation. I'm not going to go through this, but hit pause and just calculate. This is a very simple thing. I think you have like 8 data points there. So see if you can calculate the variance and the standard deviation. Hit pause now. So here's the sample variance, and of course the the standard deviation is simply the square root of that. Sometimes we don't have access to raw data in a data set, but we are given a frequency distributions. In these cases, we can approximate the standard deviation using the following steps, and this is not so far off from what we did with the mean and average. So remember, the first thing we did was calculate the midpoint of each class and then approximate the mean of the frequency distribution. This is what we did in the last chapter and section. Then what we're going to specifically do is for each class, we're going to subtract the mean from step 1 from the midpoint, which is kind of a sample data point collecting instead of the whole frequency distribution. Then we're going to square the difference. This is from step 2. And multiply by the frequency. ST2 is step 2. And multiply by the frequency. So we get midpoint minus mean. What we do in step 2, we square that and then multiply times the frequency, the number of times a response was in that distribution. And then we add all the products, all the multiplication products from step 3. And of course divide that in step 4 by n if it's a population, or n minus 1 if it's a sample. If we want the standard deviation, then of course we take the square roots of these. All right. So let's look at an example. Again, this is a good idea for you to hit pause. That's why you see the puppy pause there. Hit pause and see if you can go through these steps to find the standard deviation. Okay, this is a sample. Okay, it's a sample of 50 high school students. Okay, here you see the classes, each class. Here you see the number of responses in each class, and these will total up to 50, which is the number of high school students that we surveyed. The first thing is to find the midpoint. Okay, if you haven't hit pause and started through this, please do so. So the first thing to do is look at the class size. We go from 0 to 50. The class size is 50. So the midpoint of that is going to be divided by 2, or 25. Then when we get between 50 and 100, it's going to be 75, 125, 175, etc. So those are the midpoints for each of the classes. Okay. Then we're going to take the midpoint minus the mean. Now remember, we have to find the mean. Oh, we don't even have to find the mean. In this problem, it was given to us. So we're in good shape. All right. So the first midpoint we said was 25. So the midpoint is 25 minus the mean, 137. 75 minus 137. 125 minus 137, 175, etc. Okay, there's the class midpoints we found. Again, between 0 and 50, it's 25, 50 and 100, 75, 100 and 150, 125, etc. When we subtract You can see how building a table can make this a lot easier. When we subtract 137 from each of these values, we get this. Again, using Excel could make this even easier. Okay. Then we're going to square this difference, right, and times the frequency, which we had on the previous slide. Okay, here we go. So when we square the difference and multiply times the frequency, we get this. Okay, squared this, negative 112 squared times the frequency. Negative 62 squared times the frequency. Negative 12 squared times 13. 38 squared times 11. The difference squared times the frequency, the number of people that responded in each category. Then we add all of these products. We add all of these values together, and we get 292,800. And then because this is a sample, we're going to divide by n minus 1. And remember, we had 50 responses, so we're going to be dividing by 50 minus 1, or 49. And when we get that, we get the variance. The sample variance is 5,975.5, and the standard deviation is 77.3. Okay. So the variance, you can think of, again, remember thinking it in sort of in terms of the range, is about 6,000, the value of 6,000, but it's square units, so it doesn't really, I mean, what is a square message? You can see why that variance, the units throw it, makes it confusing. The number of text messages is really strange, whereas the standard deviation is 77 messages, and so it's in the same unit, and it makes it a little bit more understandable. And now remember, what we're saying is this is the number of text messages sent. So 10 people sent 49 or below, 5 sent between 50 and 99, 13 sent between 100 and 149, 11 between 150 and 199. So again, the standard deviation is about 77 messages from the least to the highest in terms of a unit that we can measure across. Okay. Now, this becomes really helpful when we look at the shape of data. Okay, we've already talked about shapes, and we've talked a little bit about this idea that this bell-shaped curve or symmetric curve can really help us provide a lot of insight into our data when we collect it. Okay. So this is a histogram, and here we have a single mode, single peak, and we can see it's approximately symmetric or bell-shaped, as we've talked about. Now here's where the really interesting thing comes in bell-shaped data, and this is called the empirical rule. There's a mathematical principle that follows that describes the data or where the data sits. And what this says is if your data is approximately bell-shaped, then 68% of the data will be within one standard deviation of the mean. 95% of the data, virtually all of the data, will be within 2 standard deviations of the mean. And here, almost exactly all, I wish I had the measure right here. I'll give it to you in a minute. Almost all of the data will certainly be within 3 standard deviations of the mean. There it is. The actual number is 99.7% of the data will be within plus or minus 3 standard deviations. I like this chart because then you can see it better. Remember, the mean is going to be the very middle value. It's going to be where the peak is. The most data points come from this peak, right? So remember, sigma is the standard deviation for a population. So we're saying 68% is within 1 standard deviation of the mean. That means plus or minus 1 standard deviation. 95% of the data, again very close to all, is plus or minus 2 standard deviations. And then 99.7% of the data, which is really almost all, is within plus or minus 3 standard deviations. Okay, again, you see the numbers there. You need to know this. You need to have these percentages in your head, ideally, so that you can interpret data. Okay. The following data represents projections for the percentage of population 65 and over for each state and the District of Columbia, Washington, D.C. Use the empirical rule to describe the data. Okay. So if we look at a histogram, you may not think this is relatively bell-shaped, but there is kind of a peak somewhere in the middle. It may not be the highest peak, but it does kind of go up and come down. So we can sort of assume that this is a bell-shaped curve, okay? And I want you to see this one because I think most of you would look at this and say, well, that's not bell-shaped. It's pretty flat up front, and then it goes up higher. But in statistics, this is considered a bell-shaped curve. That there's nothing that's, really high value, a lot of low values, which would make this first bar high, or a lot of high values at the very end that would make this high. So the data does tend to increase and then decrease. So it overall is an approximately bell-shaped curve. If we use technology, and here we're using the TI-84, we can see the mean is 13.249, and then our standard deviation is 1.6827 or 1.683 if we go to 3 decimal places. Okay. So now, using the empirical rule, you should be able to determine the data points that are within 1 standard deviation. So 68% of the data is within 1 standard deviation. Okay, 95% of the data is within 2, and 99.7 is within 3. Okay. So how do we do that? So I put you a little table here. So 68% of the data is within 1 plus or minus 1 standard deviation, 13.249 plus 1.683 and minus 1.683. So 68% of the data is between 11.57% and basically 15%. So 68% of the states, or the population, is 65 or older for these specific values, percentage points. Okay. When we do 2 standard deviations, now we have a wider range, and it goes from 9.88% of people over 65 to 16.62, and then within 3, almost all of the data is between 8.2% and 18.3%. And so that's how you use this kind of standard deviation to figure out inferences about your data point. And this is based on the empirical rule. 68% is within 1 standard deviation, 95% is within 2, and 99.7 is within 3. And remember, that's plus or minus because the mean is in the center. The mean can be used for samples as well as populations. When we work with a sample, we use X bar and S in place of mu and sigma. Okay. Here we have another one. So why don't you try to do this? Again, hit pause. You have a large class of 200 students. The sample mean is 65. The sample standard deviation is 10. The histogram is bell-shaped, so we know it's symmetrical. How many students had scores between 45 and 85? So based on what we just learned, see if you can answer that question. Hit pause and do some thinking about this, the empirical rule, and the percentage of data that falls between 2 points. All right, so let's continue on. Notice that our mean is 65, our standard deviation is 10, and our range is between 45 and 85, which is 20 points away from our mean, 20 points below, 20 points above. So with our standard deviation being 10, this is plus or minus 2 data points. Okay, and we know that 95% of our data, if the rough shape is approximately symmetrical, then 95% of our data is within 2 standard deviations. So by the empirical rule, 95% of the scores are between 45 and 85 for the students who took this exam. So 95% of 200 gives us 190 students. So approximately 190 students had scores between 45 and 85. Okay. Again, you can hit pause and then go through these to see which of these. Again, this is just kind of seeing if you're paying attention to when we can use the empirical rule. So I'm going to move forward these. Remember, you have to have a bell curve or an approximate bell shape in order to use the empirical rule. So another rule or property is something called Chebyshev's inequality. And if we don't have a bell-shaped curve, if we don't have a symmetrical distribution, Chebyshev's inequality allows us to look at any data set and make some general rules. It's not quite as restrictive, and so this can help us, again, if we do not have a bell-shaped curve of data. So Chebyshev's inequality states that we really only use this for values of 1 and 2 standard deviations. First off, in any data set, the proportion of data that is within k standard deviations, k equaling 1 for 1 standard deviation, 2 for 2, of the mean is at least 1 minus 1 over k squared. So if we make k equal 2, then we get 1 minus 1 over 2 squared. 1 minus 1/4 gives us 3/4. And so when k equals 2, 3/4 or 75% of the data is within 2 standard deviations. If we do the same thing for 3, 1 over 3 squared is 1 over 9. 1 minus 1 over 9 is 8/9. So 8/9 or 89% of the data is within 3 standard deviations. So again, we only really use this within 1, 2, or 3 typically for anything. So you notice here we can't really use 1, because if we have 1 minus 1 over 1 squared, we get 0. And so this doesn't provide any insight into proportions within 1 standard deviation. As part of a public health study, systolic blood pressure was measured for a large group of people. The mean was 120 and the standard deviation was 10. It doesn't indicate that we have a symmetrical curve, so we're going to use Chebyshev's inequality. See if you can calculate what it indicates about this data based upon Chebyshev. Again, you have the mean, you have the deviation. So set k equals 2, k equals 3, and solve. If k equals 2, we get x bar plus or minus 2 standard deviations, 120 plus 20, 120 minus 20. So we get values between 100 and 140. And we know 1 over 1 minus 1 over k squared, that was 1 minus 1/4, is 3/4 of the data. If we make k equal 3, remember this is 8/9 of the data, and again we have 120 plus 3 times 10, or 30, 120 plus 130, 120 minus 130, so 8/9 of the data is between 90 and 150, or 89%. Okay. Both of these principles or rules or identities provide information about the proportion of a data set within a given number of standard deviations of the mean. Again, an advantage of Chebyshev's is that you can use it for any data set, where the empirical rule you have to have an approximately bell-shaped curve. The disadvantage, of course, is that it provides a much less reliable, it's a more of a rough approximation versus the empirical. Well, there is something called a coefficient of variation, CV for short, tells how large the standard deviation is to the mean. So it's just a ratio. And what it does, it can be used to compare the spreads of data sets whose values have different units. So you want to see, like, I don't know, maybe the spread, again, what we're looking here is if we have very different units of measurement, because we're measuring different types of data points, we can use this coefficient of variation to compare the different standard deviations. Simply dividing the standard deviation by the mean gives us this coefficient of variation. So calculate these and see if you can figure out what those two values are, and then what they imply. National Weather Service records show that over a 30-year period, the annual precipitation in Atlanta, Georgia, had a mean of 49.8 inches with a standard deviation of 7.6, and the annual temperature had a mean of 62.2 degrees with a standard deviation of 1.3. First, calculate the coefficient of variation, and then for both precipitation and temperature, and then figure out which has the greater spread, and then see if you can figure out what does this mean kind of common sense wise. Again, hit pause. These are simple calculations. You should definitely try these while watching this video. It shouldn't take long. All right. So again, we're taking the standard deviation for precipitation, 7.6, divided by the average, or 49.8, we get 0.15. We do the same for temperature, standard deviation divided by the average, and get 0.02. So we can see here that the coefficient variation is larger for precipitation than it is for temperature. Okay, so we say that precipitation has a greater spread relative to its mean. What does this mean common sense wise? It means that year after year, temperatures vary less than the amount of precipitation or the amount of rain. So temperatures kind of stay much closer to their average values. They're not spread out as far, whereas precipitation has a much greater spread. So in one way, you could think that using average temperature is a better choice than using average precipitation, because the spread is not so far overall. Just one thought, I want you to kind of understand how we're using these measures and what they kind of mean. All right. So these are all the things you need to know. Again, I would definitely hit a pause here as well and see if you have all of these notes or ideas in a note sheet. If you could have one page for each section, that might really help you as you're studying for tests. But this is the end of 2.7.